Welcome everybody to a lecture series by Professor Peter Leach in the NITheCS Mini-school. This is the third lecture, I believe.
Yeah, I didn't want to interfere with your beliefs.
It's not suitable for them.
We okay? Okay. Now, what I want to do today is to talk about integrals. Now, when you have a differential equation, your aim is to solve it. And that's not a very original idea, but sometimes you can't solve it. Sometimes you can't solve it, but you can actually get some geometric interpretation from the integrals. As a practical example, right. Oops. In three dimensions, you actually obviously can integrate this. Now, the wiggle is because I'm using vectors. And when you do that, you can actually break the thing up into parts. Each part is a separate integral. And you can then look at the integral and see that it tells you something about the geometry. We'll do a deal with it. There are some others which are, well, examples. Take you familiar with the Kepler problem? Oh dear. Doesn't that help? You know who Kepler was? Don't they teach you anything? No. Kepler was an astronomer. And he used to go and look at the stars and the planets and that in some hope of understanding. Of course, he did have a slight disadvantage. What was the disadvantage?
Was he blind?
Sorry?
Was he blind?
I still didn't hear you.
Was he blind?
No, oh, blind. No, no. Why would you want to be blind for? It's not very easy to do astronomy if you're blind.
Okay.
No, he actually looked at the motion of the planets and said, there are certain conserved quantities, which is another way of saying the first intervals. So it was the regularity of the planet's orbits which led him to believe that there must be something there, because you know planets too, don't you? They're actually, they usually go around that way, not that way. Now, remember, this was before
Newton.
no,
Was it before Newton?
thank you. Yes, you can come up there and have a do it. So we didn't have all that lovely calculus stuff that Newton developed, and all those lovely mechanics things. So it was really in those days a matter of observing. You have to observe to see if there's any regularities. Absolutely. I can see myself. Now, what sort of things would you have observed? Okay, well, you get up there and you say, it's there today, it's there today, it's there today. Different days, of course. And it just keeps going around. What shape is the orbit?
Ellipse.
Thank you. You can come again. So first of all, the orbits were in an ellipse of varying degrees of eccentricity. Now, are you familiar with eccentricity? I mean, why didn't you say? You aren't supposed to ask questions if you don't follow. Right. Now, you know that the planet goes around in an orbit. What's the shape of the orbit?
I don't know.
And it looks.
There's an ellipse, thanks. Now, do you know anything about ellipses? Right. Some can be sort of almost a circle, and some can be a bit long and skinny. And what determines that? You may have to be the spokesperson.
How far the 2 points are from each other, the ones that describe the ellipse?
Well, I was thinking more in terms of how eccentric the ellipse was.
Mm.
Now, if you heard of Halley's Comet, right, okay. And you know what it does?
It comes past Earth.
Every 75 years.
Huh?
And it then wanders off into the far reaches of space because it's describing an ellipse of quite considerable eccentricity. Whereas other heavenly objects, we'll call them, they are almost in circular orbits. And you might say, well, why one and not the other? But if you're going to do that, I suggest that you ask our friend here. You know why?
No.
I don't know that. I mean, how are you going to say, well, look, there's a planet or comet or whatever wandering around? Why should it have an eccentric orbit? And why should there be different shapes. Still ellipses, but you can have a long ellipse or a short ellipse. Right. So what sort of thing, well, you won't know because you don't know about the Kepler problem. What sort of things are conserved?
By,
Sorry?
are conserved by,
An orbit described like this. Oh, I should have told you, today we're talking about integrals.
No.
Now, what are integrals? Well, it's fairly simple to answer that. They are functions of the dynamical variables which are conserved. Interesting.
If the force, the attractive force is constant, isn't it?
No,
No. Okay, it changes if it goes farther away.
Yes,
Okay,
yes.
never mind.
and what's the force proportional to?
Gravitational constant.
I suppose you could say that. Personally, I would have said it was proportional to the inverse square of the distance between the two objects. Now, you see, with the B over R, you have an inverse force. So you start looking at these things, and what do? You've got your fantastic new telescope. You're supposed to say something.
What?
When were telescopes invented?
I don't know,
Oh, good grief. Yeah, I won't ask you, Roy, you're becoming too much of the person who gets asked everything. No idea. That's a pity. I was hoping someone would tell me. Would it have been early in the 17th century? And of course, when you had your telescope, you can say, okay, there's, for example, Venus, it's there today, or tonight, if you prefer, and then it's a bit further on, and then eventually it comes back. What does that mean?
Two orbits.
Well, it's in an orbit. It just repeats itself. So I can see. And that just keeps repeating itself.
cyclic,
Sorry?
cyclic,
I can't hear you. Stop mumbling.
cyclic.
Of cyclic. Yes. Now, is it actually precisely cyclic? No comment was disturbing the car.
No.
It can vary. Now, what would make it vary?
The other planets.
Yes, that's a good one, because if the other planets get a bit close, I'm speaking astronomical distances, not that sort of person, that would disturb the gravitational field, and so they could wobble a bit off orbit. But generally speaking, the planets maintain some variation on the theme of elliptic orbit. And that is why we had that big event the other day. Remember, when we were celebrating Kepler. You remember what Kepler did?
He observed motion of planets before Newton.
If you mumble all the time, I shall have to go and get you a microphone. No, just a bit louder, please.
Okay. He said he observed the motion of planets before Newton invented mechanics and calculus.
Yes, yes, it was a matter of observation. Of course, things were a bit primitive a long time ago. How would they measure the period of rotation? That way, only this way.
Maybe they would count how many rotations.
That seems like a pretty reasonable one, and what they would realize is it's come back to the same place where it was last year.
Yeah.
So they observed this thing about periodic motion. Now, that's for the planets. Well, things like Halley's Comet, which is really quite eccentric. But what about this one over on the side? We'll take the top equation, the quite thin one. What does that tell you? It's a second order equation. And since the little twiddles underneath the R's, that means it's in more than one dimension. What is it? How do you do mechanics here?
Long time ago.
Well, I did mechanics a long time ago, and I can still remember. Now, it's an oscillator. You know all about oscillators. Bong, 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 bong. Quite exciting. And it's one of those things where you can say, what does it represent? I mean, we've just got an equation there. I've told you it's an oscillator, but what physical thing?
My job, don't.
Oh, good. Right. Now, there was something you would have learned. Oh, I don't know. At school, I imagine. You didn't do science at school, did you? Uh-huh. And did you ever hear anything about who was it?
Well,
What's going on? No. You probably have a very fancy clock at home, but once upon a time, we had things with a long rod and a weight at the end, and it would just go like that. And what's that called?
it's a pendulum.
Very good. Right. Now, what do you know about a pendulum?
it's oscillating at with a certain period. And it reduces the oscillation at some point.
Well, that's eventually, yes, but why does it reduce its oscillation?
It's so like let's say if we give it an initial velocity,
Yeah,
then the acceleration is reducing. I think it's because of the mass of the.
It's friction,
thank you, sir. You can come again.
either with the air or with the connection. Because
Probably both, I'd say.
both, yeah.
So you have friction. And look, do you think you can get rid of that face?
It's a pop-up on the
Yes,
on the
that's
computer.
problem.
I'm telling this to the audience so they don't think that you're pointing at one of them.
That was a bit quick. So, now, who first observed the pendulum is going backwards and forwards like this? Now, we have to be a bit careful there. We're not talking about the person who saw it first, but the person who actually talked about it.
You're asking who that person was.
Yes.
I don't know.
Okay. You had an interesting time with the church, actually.
Galileo.
There we go. Give you a hint and you pop in with the answer. So he observed what's known as the let me practice my Greek. Isochronous motion. What does that mean, boy?
Same period.
Right. Yes. So it's periodic.
Yeah.
Now, are there any other things which have periodic motion?
Orbits.
Yes, the orbits. I was thinking of something a bit closer to home.
Having breakfast. Everyone, we have breakfast.
That's a good one. Right, no, that is really very good. This thing is sort of go backwards and forwards. I mean, I know we realize that because of the bit of friction that the pendulum will slow down, but for a while, particularly if you have a nice support and a nice heavy bob, and what else? You put it in a vacuum, so you don't have the air resistance. But just if you're going to do that, I've got a suggestion to make. Yes, let's ask what.
What?
Huh?
What's the suggestion?
No. If you're going to put a pendulum in a vacuum, what's one thing you don't want to do? Oh, come on. You don't want to go in with it. This is very trying. Anyway, I think I wandered off the point far enough. Which one am I reading? This one. Now, with the Kepler problem, there are certain conserved, no, sorry, there are certain conserved quantities. Any suggestion as to what they are?
The period?
You have to speak up, or I'm deaf.
The period?
Right. So it just keeps on keeping on.
Hmm.
Is it possible to have such a thing?
To have what?
You have to speak up. I told you I'm deaf.
To have what?
Constantly repeating motion.
Orbits of planets are constantly
No.
repeating.
Please, Roy.
Orbits of planets are constantly repeating.
Right, that's a good one actually, because it enables you to then say, how? How come the planet can keep going around like this?
Because it's in equilibrium. Falling.
Yeah, actually, there is a point to what you're saying. I haven't thought of it. What slows things down?
Friction.
Right. Is there any friction where the planets go wandering around the countryside?
No.
Well, I wouldn't be too sure of the absolute no, Roy, but it's pretty well frictionless. So it just moves around following that lovely equation. Now, but that's actually the Kepler problem. And the one over here, of course, is the oscillator. And that's a very useful one. Why is it useful?
We used it to keep time. We used it to keep time.
Yes, that's true. And the advantage of it is that the period remains constant. See, if you had a thing where the period wasn't a constant, well, then it wouldn't be a period, would it? And you wouldn't be able to keep accurate time. Now, do you know what they use to keep accurate time these days?
No.
They have been having clocks for a couple of thousand years. Don't you remember the water clocks? Oh. That's the trouble with you young people, you've not had the experience. Now, the guidance of the clock is it keeps going backs and forwards like that. Now, how do you, well, I'm thinking of a pendulum actually. How would you then see that as giving you a periodic motion? Because it keeps going backs and forwards. Okay. How would you determine the period?
Maybe you measure how much it takes for it to go and come back.
Now, this is a matter of interest. Why are you measuring with something which you're trying to find out how to measure with? Right, but so you would observe, and then some bright spark would come along and invent calculus. And what would be the point of inventing calculus? Roy, you're really scoffing at the idea. Now, why do you invent calculus?
To determine rates of change. Things.
Yes, actually, it's so you can torture school children, university students. Now,
Well, if a piece of paper is hardware, calculus is one of the first software that allowed us to make use of the hardware to make predictions.
I hope that's rhetorical. There, you had to invent the calculus and then know how to solve differential equations, so you could then go and find out what's happening. Now, you see, if you take the equation over on the left, you can solve that. I really have a lot of trouble running.
Chair. That's
No, but I have to go and walk over there to write on it. That's the
Yes,
catch.
then you need a chair to lean on.
Oh, like the Leaning Tower of Pisa. Thanks. Another bit of green on it. You can sit on it
Mhm.
It's okay.
and probably fall over.
Multifunction chair.
Actually, these chairs are very solid.
Solid.
Yes. And they're made out of dense material.
Mm.
What is the consequence of that?
Heavy.
Right, so you're really sparking today, aren't you? Now, if you take one up there. You'll get R. You can see I don't do much writing on blackboards. What's it equal to? Come on, it's a simple differential equation. Sorry about the writing. Actually, I realized the other day, I don't really do writing anymore. It's either typing or dictating.
Ah,
Yes. Do you use the dictating package?
no.
They're very good for writing papers.
What about symbols? Math symbols.
Some symbols you can actually get it to do.
Mm.
But otherwise, you're stuck with, well, you have two options. One is that you type it in by hand, or the other is that you don't have any equations. Now, there's a slight drawback with the second one. What's that drawback?
You can't do calculus.
Can't do what?
Calculus.
Ah, well, you can't write down formulae, I suppose, that's the trouble. Yeah.
Mm.
Anyway, oh, that's not right, is it?
That's because
Why wasn't it right? I'm silent. It's a second order ordinary differential equation. If you want to write down the solution, this general solution, you need to have two constants.
And what does it say on the left side? Sorry.
It's actually R of T.
Right.
It did run into a slight technical problem. It's called a wobble.
Mhm.
No. Actually, this right more, isn't it? I hope that is marginally better. Now, what sort of motion is this called?
Oscillatory,
You have to speak up.
oscillatory motion,
Well, I know it's an oscillation,
okay.
but it has a very precise title.
Yeah, that was my guess as well.
Simple harmonic motion. Right? Now, why is it simple? Well, there's an easy answer.
Maybe it's because it's just sine.
Well, you can have a cosine there if you like.
No, but it's not squared. Oh,
Yes, you're right. It is a very simple equation. Now, here's a question though.
what does harmonic though?
Harmonic, boing, 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 boing. It goes backwards and forwards,
Okay,
and it makes a noise at the same time.
okay.
Oh. I do try, you know. Now, that's a fairly simple answer for that equation. But what about the Kepler problem?
You just change, is your mu, is that mu and
That's a mean.
what's the denominator?
That's an R.
So is it the same as R double dot?
Oh, this one, yes, it's R double, huh? You know, you heard of that guy called Isaac Newton?
Yeah,
He said that you have second order equations to describe these things. But what happens then?
but then if that R is not, then your omega will just change into mu over R, right?
Yes, I know. I was talking about that one.
Or the other one,
Yeah.
okay.
I wanted to keep it simple. And since it's called the simple harmonic oscillator, I was successful. This one, of course, is more difficult.
Hmm.
And yet, what does it do?
What do you actually, over there, what do you actually mean by R squared? Because like, R is a vector, right?
Yeah,
So what do you mean by R squared?
R dot R.
R dot R,
Yes.
and that becomes like a number,
Like what?
that becomes a real number. R dot R.
Yeah, okay, I'm sorry, I should have written it down differently. Make it. Okay,
Okay.
now. An interesting problem. Now, if I told you about this before, just tell me to shut up and I'll think of something different. Did you know that it has 3 panes there and 4 panes there?
Ah, no, I didn't.
No, well, I only just observed it, so. Right, now. That's very good. So if we're talking about a motion in 3 dimensions here, that is the scalar product of the velocity and the scalar product of the position. And it's periodic. All right, now, here's a question. It's periodic because that's just an omega squared. It's a constant. What happens if it's not a constant? Well, the wrong silence was the same as life. If it's not a constant, you're in trouble. Because you have been hard, let's say. Right. Now, so instead of having a constant omega, you've got one depending upon time. Would you think of a circumstance where that could arise?
If there's friction,
You'd have to speak up.
if there's friction in your system,
But you'd have to put an extra force in there, the friction.
okay.
Um, uh, if you have time dependence there, you have a technical problem. And what's the technical problem? Am I right to infer that you're not differential equations persons?
Yes.
That's a pity. Well, if you've got this, the original one, you can just write down the solution. Because the omega is a constant. And you would have learned that from the roundabout standard 11, I guess. No. Here, because the omega is not a constant, you've got a real technical problem. Now, you did mention that the omega space would change because of friction. But there's a more scientific way of doing it. If you have a charged particle moving in an electromagnetic field, what happens?
In radiation.
Yeah. Oh, please. I'll have to get you a speaker.
Does it emit some radiation? No.
It would indeed have some variations.
Does it emit radiation?
But now, where would you come across a situation where this would not be a constant? Have you ever heard of particle accelerators? So what you do is you construct a device, the experiment, I think they call it, and you have it included is a electromagnet which has a change in the field. Now tell me if I'm going too much into the physics for you. I'm not. No. So you have the electromagnetic field that's changing, then you have to consider this. All right. But this problem of having a time-dependent constant there, not constant, time-dependent, have been around for a long time, probably before they even invented electromagnetism. Now, I'm sure I've told you this. You get a piece of light string and a little bob at the bottom, and you clamp it up the top of one of those retort stands. And, well, actually, you don't do it. The lab technician does it. And he had a fight with his wife that morning. So he didn't tighten it up properly. What will happen?
Will start falling. It will start falling.
Yes. And so when you have a pendulum or just a stream, let's not get too technologically advanced. The period of the motion depends upon the length of the stream. Now I'm there, I can see myself. So, yeah, what was I saying?
Rate of the motion depending on the length of the string.
Oh, right. Yeah, oh, that's right. The length and the strength of the gravitational field. Which would make it very interesting if you were to go up to Jupiter and try using a pendulum up there. It would probably change the period. But you don't have to go to Jupiter to get a variation. All you do is just get an electromagnetic field and you get oscillation. It's a simple thing. So, but you know what they use these things in?
Clocks.
Sorry?
Clock. Oh no, you mean the electromagnetic part? Okay.
Yes. They use them in particle accelerators.
Hmm.
And they sort of really jazz the thing up a bit. And then what do?
They smash particles.
Yes, okay, that's fair enough. I was thinking that they would put a target in and hit the target.
Hmm.
But same difference. Now, why would you want to do a thing like that?
To see what's inside. To see what's inside.
Ah.
Hmm.
Oh, right, okay. That's a good point there. Of course, yes, you want to actually, a physical answer. you bombard the target and see what comes out. And all sorts of funny things will come out. And what would they do? Do you play balls?
Like snooker.
But I was actually thinking of this one.
Oh, balls.
Is,
Yeah.
now, what happens? You roll the ball along, and
You should knock the other one.
well, you kick it up. Well, if you can. Well, that's what they do with these particle accelerators. They bombard the target and see what comes up. And what do they find? All sorts of things. They probably don't find so many new ones these days, but back in the 50s, when they really started playing with them, they were finding a lot. Now, what would they use for the particle to do the flashing up?
Can you repeat the question?
What would they be accelerating to get the thing going very fast so they can aim it at the target?
The proton?
Well, it would use a proton, yes. Or you could go for the heavy guys and use a helium ion.
Right.
What would be the advantage of a helium ion?
Got negative charge?
Yes.
Is it? No. It's got negative charge.
Proton.
Helium ion.
Now, helium ion is positively charged.
Oh, okay, never mind.
You know. So you have a nucleus, which has an atomic number of 2, and I think it's 2 protons and 2 neutrons. So you strip off the electrons, so it's just the core of the atom, and then you jet it up, and you start hitting things with it. And what happens then?
It can break, or it breaks the others, or
Well,
they will just bump into each other, and then some will go in sort of direction.
yes, okay, that's not too bad. You could also get radiation. You know, radiation we'd get gamma rays, probably. You know about the gamma radiation.
What?
You know all about gamma rays.
No.
Well, then why didn't you put your hand up and say, I haven't got a clue what you're talking about?
I just heard about it.
Yes. Now, you realize that you're being bombarded with gamma rays every day.
No.
You mean you don't realize, or you're not being bombarded?
I don't realize.
I thought you may have been living in a lead-lined house. Where do these gamma rays come from?
sun.
Right. Thank you. You're setting a very good example for these little people. So then back, actually a fair while ago now, isn't it? About 70 odd years, when they started really getting excited by these machines, where they could do experiments. And oftentimes use protons, or better still, alpha particles. You know what alpha particle is?
I've heard about it, but I don't really
Well,
know.
then why didn't you ask?
Because you asked me first.
No, I mentioned alpha particles. And then when you started giving me your famous blank look. Yeah, the advantage of alpha particles is that they are bigger and heavier. So you can jazz them up and then duck if they come up running after you. Now, oh gosh, I really wanted to put it there. Now, if you see this one, which is sort of the solution of that, you can actually describe what the motion is. Boing, 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 boing. Right?
Peter, will we be able to solve this kind of equation with Lie symmetries?
The top one, of
Yes.
course.
What about the second one?
Well, that's the first integral at the bottom of the top one.
I actually don't quite understand why it's an integral, because if we differentiate the left-hand side bottom expression, shouldn't we also have shouldn't we have an extra term?
Well, have you ever heard of integrating factors?
No.
Yes. Is that yeah?
So you take the scalar product of the top equation with r dot,
Yes.
and then integrate happily.
I see. That's right. Yeah, R dot cancels out. Thank you.
No, it's okay.
We are at the end of our time. Shall we continue next time, or do you want to go over time?
When you say next time,
Next Wednesday.
next Wednesday I'll be somewhere else, I don't
Is this the last lecture then?
think so. I actually don't know. In fact, I meant to ask someone that became distracted. First of all, I have to go and ask Nelly, I think, isn't it? Just whether I'm flying back tomorrow or what, I don't know.
We should ask this to Renee, I think.
Really? Oh, okay.
Yeah.
We're waiting on it. You know, I hate these things
Why do you hate those things?
because my first experience of it was in a private aeroplane when I was going to the States to do some work. And I heard this rather raucous squawking, and this woman of some size pulled out this thing, and it was also some size, and she started squawking into it. And I thought, that's really interfering with my peace and quiet.
Mm.
Originally, it was a few years ago, but they have become smaller. I'm not used to it. Right. Now, what I wanted to mention was, okay, so we've got an example here. You actually have three possibilities. You see, because your R is in 3 dimensions. And so you could think of it in terms of an X component, a Y component, and a Z component. And so you'd have 3 quadratic intervals, each with their own character. And if you start playing with those intervals, you can actually get the orbit equation. Now, I don't mean integrating, I said playing, because they have properties. And they're quite good. But now, what would happen if instead of you had the constant omega, it was depending upon time? Well, if you multiply it by R dot, scalar product, of course, would you then integrate it?
Not,
Just by looking at it.
yeah.
But as I said before, it's an important problem in particle accelerators. Now, one of the things about particle accelerators, I mean, the engineers just build them, but other people actually like to know something about their properties. And if there's a T in there, you can't do that integration. So what do you do? Yes,
I don't know.
You
I don't know.
severe technical problem.
But Lee, is that when we use Lie symmetries?
Actually, that's a good point. Yes. A very good point. Did I tell you about packages?
Packages. Computer packages for calculating Lie symmetries.
Yeah, what else?
You did, yes.
I did do that. Okay. They're very useful. I mean, once upon a time, I used to do all this by hand. But then I think with the passing of time, I was being, shall we say, getting a bit tired. So that's when there are several computer packages. I mean, there are things like reduce, which is like a generic thing. But there were some packages designed specifically for dealing with differential equations. Did I mention program Lie to you?
That specific program, no.
Well, let me think now. About 40 years ago, no, it's longer than 40 years ago now. There was a chap at the CSIRO in Melbourne who wrote a program for calculating symmetries. It was called Program Lie. And to be honest, it was a bit horrendous, but it did give results. And so one could actually contemplate looking at some of these difficult equations to get some sort of result. But one of the other things were, of course, is if you have the time dependence there, you can actually find an interval. Even though you've got the length square t there. Of course, it's a bit more complicated. But it's quite good. All of these things are quite good. Okay, well, I think we'll call it halt. I shall make inquiry. And of course, I did make inquiry, that's true. Otherwise, you may have a problem. Okay, all right. Are there any questions? You don't have any questions, Roy?
I have a question. We have the V-symmetry method, right? The research in this area, is it mostly concerned with identifying new types of equations where the method can be used, or is there also some research that's concerned with extending the method to maybe?
Okay, that's a fair question.
Yeah.
I think these days is probably more just working on new problems, because the actual possibilities have grown over the years. I mean, some of the calculations do become quite difficult, but they do have an answer. But usually, it will come out with some sort of first integral, subject to a mysterious function solving an equation. That's typical of what happens. The problem I was talking to you about, the particle in the electromagnetic field, is one of those ones. But with persistence, it was solved. Of course, the trouble was, that problem was solved without that you could solve another one. Yeah. Yeah. All right, now, you said I should speak to Brennan.
Yes, let's first conclude the lecture. Any questions from participants online? If you have a question, you're welcome to write it in the chat. And I see that there are some things that are written in the chat. So I will read them. This was actually an answer to one of the questions you asked in the middle of the lecture. We missed it, so let me read it now. Charged particle in electromagnetic field gets deflected due to experiencing the Lorentz force. There are some question marks there. And then somebody else responds to that. No, I think Professor Leach is trying to ask about angular momentum, the momentum of inertia of an object, about an axis of rotation, and omega times radians minus 1 is its angular velocity about that axis. And another comment there was CERN in Switzerland.
Not the only place, but everyone knows about. I think they have a couple of places in Russia, or maybe these days in China.
But it seems that there are no further questions or comments online. So then we will conclude here. Thank you very much for everybody joining, and thank you to Professor Leach for his lectures. We will update you through NITheCS notifications whether there will be a fourth lecture or not. We're not entirely sure about that right now. Bye, everybody.
Let me have you.